Good evening. I'm delighted to be here and to have this opportunity to talk to you about the geology of the River Esk. I start with an apology because I did have grand plans for this talk, but actually, when I came to put it together, I discovered there was so much that I wanted to say that actually it should probably be a 6 week course or something like that. But I hope you're all free until midnight anyway, because we've got quite a story ahead of us. And I really like thinking about the processes of geology. And I think John Playfair very nicely summed up the magic, the amazing giddiness of looking into the abyss of time, looking into deep time. John Playfair was a friend of James Hutton's, and wrote that about visiting Sicker Point, which I'll mention briefly, although in fact it is not in the River Esk catchment, but such an important site, of course, it needs to be mentioned. I think also I would like to channel, and I'll try and not have too many bad river puns today, but I'd like to channel Norman MacLean as well, because I spent a bit of time in America and was very drawn to his writing. And his book, A River Runs Through It, was turned into a film which captured very much the nature of rivers. And that's what I'd like to consider today, to think about what has happened in this area in the past, the geological processes, and explore the river's water in various forms, actually, liquid, solid, and gas, as we shall see, which has flowed in this area. We will consider a full suite of geological time. And rivers are crucially important in how the earth works. One of the big surface processes. James Hutton realised that. He spent quite a bit of time farming in the Scottish borders, and was well aware of the effects of erosion on his fields. But he saw it as part of a bigger pattern, where the river in flood was carrying away a part of the land, but it was going into the sea to be transformed eventually into new rock, to be uplifted into new land as part of his great cycle. So I love the River Esk and its area, but I think we do have to acknowledge that Scotland is a sorry scrap of land, really, compared to some of the other parts of land elsewhere in the world, and indeed how Scotland used to be in the past. So our rivers maybe aren't majestic, but I think there's a lot that we can see in the River Esk that echoes this big pattern, this big process of erosion and change, which is what we're going to explore. We'll start, though, going a bit further back in time, to a very different world. 450 million years ago, the yellow circle shows us the approximate position of most of what now makes Scotland, on the edge, in fact, on a corner of the great continent of Laurentia, which includes North America and Greenland, sitting at the edge of the Iaptus Ocean. I'll refer to various resources, leaflets and books and websites as we go through, and I'll put them all into a list and send them to John afterwards, just to circulate with the recording of the talk, because there's a lot of really good information out there. But this Iaptus Ocean, and the very different map of the world from 450 million years ago, it starts our story with the foundations of the Midlothian area, because there are some hints of rocks, mostly buried under younger rock. There are some hints of the Iaptus Ocean in the Esk. So if you go into the Pentland Hills, just to the south end of Black Hill, just at the very, very edge of the River Esk catchment. In fact, I think this probably is the watershed. But there are, poking up here and there, old grey rocks, very contorted, but layers of sediment that date back to this time period of the Iaptus Ocean. they're better exposed just a little bit further east, and you can see the layering here. And this is one of the resources, a whole set of resources I'd like to highlight, the Pentland Rocks leaflets, produced by the Lothian Borders Geoconservation Group. And there's about 30 leaflets cover the Lothian and Borders area. So there's lots to explore. They're all available on the Edinburgh Geological Society website. And what these sediments, these sedimentary rocks tell us about the Iapetus Ocean. They tell us that oceans in the past operate much in the same way as oceans do today. And they give us a glimpse into our first big flow of material across this area. Because the story of these grey rocks, which we find sticking up here and there in the depths of the Pentlands, probably underlie the rest of the area, although we're not too sure about that. But what these rocks show is this process of sediment moving from the land into the sea. Rivers dump sediment close to the shore as the currents slow down. But as it piles up at the edge of the continental shelf, the rocks tell us that in the Iapetus Ocean and in the oceans of today, that there's occasional collapses and a flow of sediment, sand and mud and gravel, which is transported further out onto the seafloor. So each layer of black rock that you see in these areas is representing this instant of time of a flood of material into the deep waters of the Iapetus. There's more to that story. It's not particularly easy to see, but if you head upstream from Carlops, there are some really quite important fossils buried deep in the North Esk inlier, and they actually show some of the, as well as the deep water stuff we've been talking about. You see some of the closer to shore and some really important fossils. There is a leaflet, the Esk Valley leaflet, which is produced by the Lothian Borders Geoconservation Group, available in the same place. And I'll be referring as we go along to this map on the screen. That map comes from the leaflets. And these really old rocks, older than 420 million years old, crop out in the Pentlands, just these two little purple areas on the left-hand side of the map. So it's a small part of the overall picture, but really a nice glimpse back into a deep history of this area. You can see these rocks a lot better on the coast. So if you head down past Dunbar and Coburn's Path, that's St Abb's Head at the top of the screen, just sticking out there. So it's in that area, these beautiful grey layers. And I mention this area because of the importance of this section of coastline for James Hutton. And no Scottish geology talk should forget to mention James Hutton's, born in 1726 in Edinburgh, known internationally as a father of modern geology, but a very interesting character with a very deep and varied knowledge and enthusiasm for a wide range of subjects. 1726, we are approaching tercentenary of his birth, so you'll hear hopefully a lot more about James Hutton over the next couple of years. But this is the section of coast that he explored by boat with his friend John Playfair. This is where Playfair wrote about staring into the abyss of time. So this little rocky promontory in the middle of the screen is called Sicker Point. And again, there's another leaflet from the Lothian Borders Geoconservation Group, which tells you what you see there, and it's a junction. It's a junction between the older contorted rocks, the Silurian age grey-wacky layers, which were formed on the floor of the Iapetus Ocean, and what happened next. Because the Iapetus Ocean, you may have noticed, is no longer on the map of the world. It disappeared because the continents on either side of the Iapetus Ocean moved together and collided and built the mountains that we see the remainders of in the Highlands of Scotland. They also built the southern uplands, and then in turn these rocks were buried under accumulation of new rock, the old red sandstone. So that's an important contribution that Scotland's geology has made to the understanding of the world. James Hutton's name is well known and echoes around the world. But I mention it in terms of what we're thinking about today because it tells us about what's deep beneath our feet. It tells us about the changing conditions that have happened in this area and the way that different sets of rocks have gradually accumulated. Because that really is the story of the richness of the landscape of this area and the nature of the River Esk comes from this combination of different rocks. So we've looked briefly back to the Ordovician and Silurian times, coming to an end about 420 million years ago, followed by the Devonian period and the Carboniferous and then the Permian. And as we go through today's talk, I'll guide you with you'll see these times and the colours coming up at the edge of the screen, just to help trace our way through this story. And for the Midlothian area, the next big thing to happen is volcanic activity. And we see the remains of that volcanic activity in the Pentlands. But again, we're just getting a little hint of a much bigger story because probably similar volcanic rocks to the ones we see in the Pentlands underlie the whole of central Scotland. I'm not too sure about that, but it is likely to be the case. So this is igneous rock. Igneous rock formed from volcanic activity, formed from the cooling of magma or lava and crystallizing. The igneous rocks are tough. That's why the Pentlands persist today as a solid lump of rock. That's why they've lasted for so long, because of the toughness, the nature of this igneous rock. We'll come on to the sedimentary rock, which underlies most of Midlothian. Most of the River Esk flows across sedimentary rock. And after the volcanic activity we see in the Pentlands, there was a long period of accumulation of sediment as well. But we'll come to that. First of all, the volcanoes. Dating from about 420 to 400 million years ago. What we see in the Pentlands is just a small part of a much bigger story. Most of the granite you find in Scotland, mainland Scotland, is formed during this time period. We've got big volcanic eruptions at places like Glencoe and Ben Nevis and Cheviot, as well as the Pentlands. And so when you're on top of one of the Pentland hills and looking out over this landscape, actually, for a geologist, it's a little bit frustrating because there isn't a lot of rock visible. You do see occasional screes, but the underlying structure of the Pentland Hills relates back to a vast episode of volcanic activity, of lava flows, but also of volcanic explosions. The picture on the right is not from the Pentlands. You'll not be surprised to know that's from Montserrat in the Eastern Caribbean, where I spent a couple of years monitoring this volcano. And I include this just to get an idea of what the Pentlands might have looked like in eruption. The rock is very grey, and the problem with this kind of volcanic eruption is the presence of pyroclastic flows. So this little cloud coming down the hill here is moving fast. It's fragmented rock. It's heating up the air. It's carrying steam with it. It's very, very dangerous. Here's another picture of the aftermath of a pyroclastic flow, which you can see has ripped the roofs off houses and killed off the vegetation and left behind a layer of volcanic ash. So this is our second type of flow across this area, this time certainly containing steam and very hot. But there would have been repeated eruptions of this kind of volcanic activity for probably certainly millions of years. It's difficult to put an exact boundary on that, but around about 410 million years ago, for probably a few million years, there was eruption after eruption that builds a carpet of volcanic debris, some of which has been preserved and we see today in the rocks of the Pentlands. As I say, the rocks are hard to spot, but there's plenty of evidence of it. I think to look for these light-coloured screes, very different from the basalt that you'll see at Arthur's Seat, which was a later volcano. This is silica-rich volcanic rock, and it breaks up into sharp-edged pieces, it really does a very good job at disguising the majesty and the power of the creation of this stuff. It's very old, of course. It's more than 400 million years old. It's had quite a history. It's had a lot of alteration after it formed. So it doesn't really capture the full story very well, but it gives us a glimpse into the past and another layer of rock added into this area and helping to contribute to the diversity of not just the rock, but the landscape that's resulted from it. We looked at the 450 million year old map a minute ago. We're moving forward in time, and the Iapetus Ocean has closed. By the time we get to the upper map here, everything is coming together, and Scotland is part of a much larger continent that is either called La Russia or Euramerika. So Britain brought together for the first time around about 400 million years ago, and located just a bit south of the equator. These changes are coming together, the closure of the Iapetus Ocean. By 400 million years ago, things are changing. The volcanic activity is dying down, and this area becomes much more continental. So having been at the edge of the Iapetus Ocean, we then enter a long history, which is quite foreign for us in Britain to imagine being in a continental setting. But this is what ushers in the possibility of large-scale continental processes, particularly the erosion of high ground and the transport of material in James Hutton's rivers towards the sea. And for this area, we need to really see this, what we see today in the River Esk as being just a very small part of a much larger picture. There's another big change going on at that time, which is a worldwide change and a fascinating time period, because these two maps on the right-hand side show the greening of the land. Life had thrived in the oceans for billions of years in different forms, gradually getting more complex. But it's only around about the Devonian period, maybe a little bit before that in a small scale, but it's really only in the Devonian period and into the start of the Carboniferous period that life really gets established on land. And wow, what a change. And this transformation with going from just small plants existing in wet areas close to the sea and ponds to the land being covered. And it just so happens this time period also has a lot of land round about the equator, nice and hot with today's climate pattern of rainfall at the equator. Brilliant conditions for life to thrive, and we capture that story beautifully in the sediments that started to accumulate on top of the new formed continent of La Russia. And here's a picture to try and demonstrate and show some of this. It comes from a resource the Edinburgh Geological Society produced for schools, and Alison Timon drew this drawing for us. On the left, the highlands made of old metamorphic rocks and high ground, rivers flowing from there towards the sea, volcanic activity going on as well. But for the story of Midlothian, the volcanic activity is buried, so we don't see it. And really our story is of the accumulation of sediment and a pattern that goes on for over 80 million years because the centre of Scotland, the central lowlands were just gently subsiding all during this time. So there's high ground to the north, there's high ground in the southern uplands as well, and a material being washed from there and to build up this lovely carpet of sedimentary rocks. So where you see rock along the River Esk, it is sedimentary, and you often see the layers. It's relatively soft rock, which is why overall the Midlothian area is lower and the pentlands are high. An interesting time in Earth history. Really nice conditions to form a mixture of different sedimentary rocks depending on the conditions. And this is a mix of rock that's been useful for people coal principally, but also the limestone. It's been used for mortar and for improving the agriculture, sandstone for building. So a mix of rocks accumulating in this area gradually over time, layer upon layer. And the rough rule of thumb, when you look at a little cliff like this, a couple of meters high, the rough rule of thumb across the whole period is it takes about 10,000 years to form each meter of rock. So there's an awful lot of time has passed in the accumulation of these layers by the slow processes of rivers eroding and flowing and depositing material. And I'd try and just kind of give you a flavour of the geography. This is based on a diagram from the Geology of Scotland book, and it shows the Highlands as high ground, Southern Uplands as high ground, and centre of Scotland in a very interesting position, really between land and sea. The overall pattern remains the same, with high ground to the north and the Riek Ocean to the south. That persists for tens of millions of years, but in detail it varies a lot. So the kind of middle zone here, there's a lot going on. There's quite a bit of volcanic activity. This map from 340 million years ago shows the volcanoes erupting on the west, forming the Campsie Hills and around about Glasgow. But for our area, we've got subsiding land and layers of sand being brought from the north, and sometimes sea level being a bit higher and flooding across the area, other times the sea being a bit further away and rivers flowing across fairly low ground, wet, swampy ground close to the sea. But these are really nice conditions for an interesting variety of sedimentary rock to form. And we see it wherever we get a chance, particularly the layers of sandstone tend to be a little bit more visible, a bit more resistant to erosions. This is in Habby's How, a very typical pattern. You see at the base of the cliff there, there's a bit of an overhang, and that's because the layer underneath mudstone a little bit softer and it's been worn back. That's a really common pattern to see some of the rock, but we don't get hundreds of meters of the same kind of rock. Over time, the conditions change and different types of sedimentary rock form. And very nice rock it is as well. This is also in Habby's How. Beautiful soft sandstone. You run your fingers over the surface of this and you feel the grit. And most of these grains of sand are from the north. In the sun, you may catch a glitter of little mica crystals, some of which apparently come from as far away as Norway. But we've got that record of conditions of rivers traveling a long distance, bringing with them a sediment from the breakup of older existing rock, but it's the quartz grains that survive, and they get worn down and they're nice and smooth and uniform in size, and they build up in these sandy layers to make the sandstones. And Roslyn Glen, sorry, before we get to Roslyn Glen, there is limestone as well. It's not very prominent in many places, and again it tends to just be individual layers. Here's a nice example forming the waterfall at Peggy's Pool and Habby's How, and indeed if you go and have a look at that, you will see crinoid fossils in it. So that's formed by undersea. The sea has been here, and that's formed limestone. The very similar limestones crop out over Vogrie as well, Crichton Castle. And again, you get this evidence from within them of the sea conditions, the seabed conditions, and the fossils that are there. But our main story, particularly exposed very nicely along the Esk, is of rivers, and river flow from the high ground. Again, thinking of this little bit of Scotland as part of the bigger whole of the massive amount of land that lies to the north. There is no Atlantic Ocean. So the animals of this time, the tetrapods with their little stubby legs, theoretically could have walked to America. They could have walked upriver to Scandinavia. They would have. There was this whole continent stretching north and west from here, and continents produce rivers, and rivers flow towards the sea. So this interesting zone between land and sea, where the rivers are bringing sediment and depositing it, helped by the fact that the land is slowly subsiding because of the big tectonic picture, the volcanic activity. I do find it quite amazing to think about these rivers of the past and the flow of water that has gone across this landscape for tens of millions of years. Everything is in its way to somewhere else is very true geologically, and certainly in the case of this big geological process of sediment being moved by flowing water. And I went looking today on my computer for pictures of Roslin Glen because it's a place I love and I go to a lot. And I didn't have many good pictures because it's not an easy place to take pictures of. But I turned to my good friend Geograph, which is a fantastic website of pictures. Photographers collect pictures, submit them to this website. Every part of Britain is covered, every grid square is covered. And I thought there'll be some good pictures in there, even if I don't have any. Actually, it's not just me that finds Roslin Glen hard to photograph, but it's better to be explored in person, of course. And if you go to Roslin Castle and the path that takes you down beside the river there, absolutely fantastic cliffs of this thick units of pinkish sandstone, and the modern river cutting down through it. And James Hutton, as well as appreciating the geological process of rivers and transporting material to the sea, also said that rivers were very useful when cutting down through the rock and exposing it for us so we could see it. And that's one of the great things, particularly at Roslin, we can see this beautiful thick layer of sandstone. You go a little bit further upstream to the gunpowder mills in the upper part of Roslin Glen, and you get what is the finest rock exposure along the Esk, this beautiful cliff, and I do have lots of pictures of it. But what this shows us is a transition from accumulation or slow accumulation of thin layers of mud and a bed of sand to this area being affected by larger river channels. And these river channels have had enough power to cut down into the existing sediment. So each of these little scoops at the bottom of the cliff here is the result of a channel filling with sand. And this is sand that's come from the far north and is accumulated within these little channels as part of a big river system. So this is a really good example of that variation in rock type. The rivers don't just deposit sand. When they're in flood and they spread out and cover their floodplain, there's a lot of accumulation of finer sediment on the edges and in any one place. As time ticks on, it'll go from having the main river channel and sand accumulating to other times when the conditions are much quieter and swampy, and there's just a slow accumulation of mud. So that's what that lovely outcrop across from the mill on the banks of the River Esk really does show us very nicely that transition from slow, muddy conditions to these powerful river channels carrying sand. And these river systems, this big pattern of movement of material isn't just important in terms of the kind of rock it gives us. It's also really important in the environments it creates for life. So the Carboniferous period is named from the carbon from the coal that was found within it. And it's a great illustration of the creation of the right conditions to allow life to thrive. So in a river delta system like this, with river slowing down and spreading out as it comes towards the sea. We've got lots of different environments and lots of space for plants to grow. We're on the equator by now, middle part of the Carboniferous, 338 million years ago. It's nice and steamy. There's lots of nutrients in the system, and there's lots of areas where forests can thrive. So that's where the coal comes from. And just like the other sedimentary rocks in the sequence, it doesn't occur in great thicknesses. It is just here and there, 1 meter or 2 meters thick, mixed in with these other rocks, but representing this really dynamic and changing environment between land and sea. This is a more complicated diagram. Apologies, you won't get all the detail from this, but I did want to just share it because I love what it tells us about the surrounding area. You have to look hard to find the coastline in Edinburgh over to the west there. The blue line just to the north of Edinburgh is a modern coastline, and you can pick it up further north. Places like Kirkcaldy and round to St Monans are on the coast. But the blue strip running across this map is the Midlothian Leven syncline. So this is the basin where the coal is found, and it runs across the Firth of Forth, under the Firth of Forth, a deep basin filled with these varied layers of different rocks. Incidentally, the yellow on this map, and for some reason, the yellow is used for this rock unit and all the Geological Survey maps. This is called the passage group. That's the sandstone layers that you see at Roslin Glen, and you can pick them up in many other places around the Firth of Forth, a time period when the rivers were particularly prodigious in producing sand and a nice thick layer of sand without much variation within it. It's called the passage group because it lies between the two main coal bed areas, and was an interruption between the two of them. But anyway, this coal basin underlies much of the River Esk, and is really in a basin or a bath shape, and that's really important in terms of how these rock layers developed, but also in terms of how the coal was won from underground. It's hard to spot coal these days. There is a wonderful exposure of a thick coal seam just right underneath the bridge in the new A68, the Dalkeith bypass. It's mentioned in the Esk Valley leaflet. You'll see this picture in it. It's actually kind of hard to get to see it, but it's really, really nice that it's there. And this is unusual because most of the coal that was easily accessible, of course, was mined long ago. And the cross-section from the British Geological Survey map across this area, so running from, in this case, from Arthur's Seat or the Pentlands, running eastwards, straight across the area, demonstrates very nicely this basin shape of the coalfield. The yellow line again of the passage group, the yellow seam, and it goes down to about 1,200 meters on this cross section, and you can see it's just some of the coal seams are picked out here. The one down at the bottom is the North Greens coal. There were other coal seams deeper than that as well. And this demonstrates really nicely the geological structure, but also the history of mining, because early mining of surface layers was often on seams that were steeply tilted. This cross-section is vertically exaggerated, so the tilt is more extreme than the reality. But even so, these were layers of coal that were disappearing underground at a sharp angle, and they dug them out as far as they could, and then the holes flooded, and actually then they developed the technique of putting in a vertical shaft and going at it from below and working upwards. Hard work, though. But of course, understanding the overall structure, people realized that these same layers that were steeply tilted at the surface would go down and flatten out in the middle of the coalfield and then come up on the other side. So the big prize from the 1950s was to put deep mines through all the upper stuff, through the passage group, and get into the lower coal seams where they would be flat and extend for miles and be easy to follow. That was the plan. And of course, they succeeded in getting to the coal seams and exploiting them for at least some of the planned working life of these deep mines. But it was difficult. The geology was difficult, and water was difficult, and of course the political situation needs not to be mentioned. So we've got this amazing selection of rocks from the Ordovician period through to the end of the Carboniferous, 150 million years of geological time recorded in this area. And we get to see this variety partly because of the Pentland fault line. So this is the biggest fault line running through the Lothian area. It's got more or less a north-south trend, and it defines the edge of the Pentland Hills because it defines the edge of the hard rocks of the Pentlands as opposed to the softer rocks of the Midlothian coalfield. The fault has been around for a long time. So it's not something that's been superimposed later on the rock. So that's an important part of the story of the Midlothian syncline, because this thick accumulation of sediment that we have preserved in Midlothian, part of the reason we see it is because there's so much of it. And that's because of the conditions at the time it was forming that allowed in this one spot, in this one place, for an extra accumulation because there was subsidence, because this fault line was active then. So it's a big part of the story in the original formation of the rocks, but it's also a really big part of the story and how the landscape looks today, because of movement along this fault line has ended up with two different sets of rock now sitting next to each other at the surface. So fault lines are good at doing that, and good at moving rock around. And in this case, the rocks underlying the coalfield have moved downwards, or the Pentland Hills has moved upwards, depending on how you want to think about it. But the point is that if you were to go right down through the coalfield, right down through all these younger sedimentary rocks, we're pretty sure that deep underneath Midlothian, you'd find more Pentland rocks, find more volcanic rocks, deep underneath all the coal. And it's this movement of the fault line giving us different kinds of rock at the surface, which really creates the whole nature of the Esk catchment today. We've got to 300 million years ago now. The end of the Carboniferous period, the start of the Permian. And there's two big things happening. First of all, Britain is continuing its journey northwards. You'll have noticed we are no longer at the equator. So that brings in climate change, just because of the change in position of, relative to the climate system. So it starts to get drier. So the river flows stop. But there's also the overall changing pattern of the world, the formation of the Pangaea supercontinent. And that brings to an end this process where things were stretching and thinning, and the centre of Scotland was gently sinking down. So that ends the conditions for the formation of new rock. So we're just a little bit to the west of where the Esk flows into the Firth of Forth and Musselburgh. Underneath the muds and the gravels and the sand there is the youngest sedimentary rocks in this area. The upper coal measures from just the very end of the Carboniferous period. There was more rock though, because we've had 300 million years of erosion. And that means for most of 300 million years, rivers have flowed across this area. Not all the time, not always in the same direction, but we've had this really, really long time period. I do, again, find it so amazing. If you were to adopt the philosophy of Winnie the Pooh and just stand and stare for a minute or a century or a million years. So much of what we see in terms of the overall geography of this area has been gradually established over this huge amount of time by the operation of water flowing across the landscape. I said if you go to Musselburgh, you'll find the youngest sedimentary rocks in this area. There's another bit, which is a very well-known crag at Carlops. And there's a little bit of uncertainty about this, but it's possible this is very, very different from everything else. It's certainly very, very different from everything else through the Midlothian area, but it's probably 60 million years old. It's probably an injection of magma from deep down associated with volcanic activity on the west coast of Scotland. Only 60 million years old. It's trivial, very young. But that is an interesting time for Scotland. The Atlantic Ocean starting to open with volcanic activity, forms a lot of rock over on the west coast. But also this brings in the sort of overall pattern of drainage across Scotland. So we have to think about the last 300 million years of most of this land we're talking about being hilly, dry land above the surface of the sea. Certainly there's been times the sea level's been higher, but most of the time, most of Scotland has been dry land for 300 million years. And it's had rain falling on it, it's had rivers flowing across it, has had sediment removed, rock removed. A lot of that has gone into the North Sea, which has gradually developed over this time period. And the layers of sedimentary rock on the floor of the North Sea are recycled from the surrounding land. And then the Atlantic Ocean opening as well means that it gets sediment being transported in that direction. Amazing long time periods of geological processes. And you've been waiting for the Ice Age, I know, because everyone loves the Ice Age. We can imagine this brilliant story of ice carving over the landscape, creating the corries and the U-shaped glens of Scotland, and eroding rock. Yes, our landscape is glaciated, but actually, a lot of the features of the landscape go way back beyond the Ice Age. The Ice Age is only the last 2.5 million years. So there's been a lot of time before that, where the overall pattern, certainly probably for tens of millions of years, there's been sea roughly in the Firth of Forth area, and certainly rivers flowing in that direction towards the North Sea. And so our more recent geological history is certainly probably having rivers coming from the high ground of the Pentlands, because there's hard rock there, and the high ground of the Southern Uplands, because there's hard rock there, and rivers flowing north across Midlothian towards the sea. But the ice does a lot. It does a lot of eroding. It exposes the hard rock of the Pentland Hills as it scrapes across there. A lot of the lines in this map, incidentally, this is a great resource called the Brit Ice map. You'll find it online. A lot of the lines in this map are direction of ice flow, and we've got an interesting zone here. Across Edinburgh, most of the ice is Highland ice coming west to east, but when you get a little bit further south, there's a lot of flow in the Southern Uplands. And I don't need to tell you much more about this, because I know you must all have studied this lovely information board. I think it might be the only geological information board on the River Esk. It'd be nice to have some more, but I think I see the hand of David Sugden in this, and I'm sure you've heard him talk, and I'm sorry not to give more attention to the moraines of this area, but do go. This is at the Maiden Castle, just up from Hewan Bank, Bolton Mill, yeah, just at the top of the slope there before the path descends into the Maiden Castle. Go and have a look at this, because it's a really good board, and it gives a very good story. It gives a good demonstration of the story of ice moving across this area, and two different sets of ice really battling it out across and depositing. Because ice doesn't just erode, it also deposits. And there's a lot of the surface material we see along the River Esk, which is the result of the material moved by the ice, and then as the ice melts, moved further by meltwater. And that's another big part of the story of the shape of the land. We have a lot of examples of these meltwater channels. This one's at Carlops, but there are plenty more, and they're easy to spot because they're nice, wide, low valleys, flat bottoms, and the stream that flows through them now, the Burn, is very small compared to the size of the valley. So you can see that even in flood, the current water flow would not be eroding a feature like this. So this is an echo back to the time when the ice is melting, and yet another flow of water across this area, helping to shape the land. In the same place, turning just to look downstream, you see how the water's kind of gathering into a steep-sided gorge going through Habby's How, and then further downstream at Roslin as well. There's plenty of places where we can see these steep-sided rock gorges with the river in it. But today's river, not enough power to carve these features. So these are echoes of the time when there was a lot more water moving across this landscape. And the Brit Ice map shows that actually a lot of the meltwater was flowing eastwards. So a lot of the blue lines in this map across particularly the area of the South Midlothian, there's a lot of lines running eastwards. So actually the drainage pattern that we've got today is re-established on the old landscape after the ice has melted. But as the ice was melting, there was a lot of water flow being blocked from going down to the north and heading eastwards. So you get a lot of these channels fairly dry coming through the Pentlands and across Midlothian. And to a large extent, this is a landscape that's still recovering from the last glacial period. We're still within the Ice Age, and the ice melted from this area about 15,000 years ago, which in geological sense is very, very recent. And you see that at places like Huon Bank, where there's ongoing landslipping of these sands and muds, the glacial deposits. And it reminds us that the Ice Age and our time on the Esk is very short. This is just a snapshot in geological time. This landscape continues to evolve. And one of my favorite bits of James Hutton's writing, it says it's about imagines a shepherd or the farmer sitting and looking at the landscape and just imagining the landscape to kind of be fixed and always to have been there. But the man of scientific observation sees great changes that have been made and foresees a different state that must follow in time from the continued operation of that which actually is in nature. So this was James Hutton's big idea, to look at the landscape and to see the physical processes that had happened to bring it to this point. I started by quoting Playfair, James Hutton's friend, staring into the abyss of time, the ability to look back and to see the conditions of the past. But Hutton was also able to look forward and to imagine how this would continue to change in the future. So I'll leave you back at Habby's How, and I hope this very brief introduction to the geological underpinnings of the River Esk has given you an appetite to explore more. There's loads of good resources to find out more about it. And I think to see the modern river that we all know and love, to see it as a combination of everything that has happened here, the formation of different rock types, the movement on the fault, the conditions, the changing conditions that have allowed different rocks to form, this long period of erosion that's created the landscape. It's all connected, it's all part of the whole of the system. And that's a system that will continue away on into the future. We can't predict the future very easily. Humans aren't very good at looking forward, but the patterns we see here, geological patterns of land and sea and erosion and transport of materials, these will continue. This area will be land for a long time to come, and rivers will continue to run through it. I'll finish there. Thank you for your attention. I'm very happy to answer any questions, and on the screen, just some of